So in this lecture, we will discuss about the common collector amplifier. So as we know, the if you see the BJT is a three-terminal device. Okay, so we know that this is my emitter, this is the collector, and of course this is the base. Okay, so and of course we have one input and one output when we discuss about the amplifiers, right? And in the common emitter, what we have seen that we have grounded the emitter, okay, and we have provided the input at the base and collected the output at the collector. Okay, of course the biasing is there. We need to make sure that the base and the emitter should be forward biased, and the collector and the base should be reverse biased. Okay, so in the common collector circuit, what we are going to do that um, instead of collecting the output at the collector, we are going to ground it. Okay, so that's how this is a common collector, and then we are going to observe the output at the emitter. Okay, but then again we need to meet the condition, that the DC biasing condition, right? So if I want to make sure that this is in the forward biased and this is in the reverse biased, and because this is at a ground, we have grounded it, so my this base, the DC voltage should be at negative potential, and this also should be at a negative potential. Okay, but we may not like to do so, because the thing is that the battery, we always consider, with respect to the ground, so we may not want to ground the collector instead, and or use negative potential. Instead of that, what we'll do is we'll use a positive potential at VDD at the collector. Okay, so which means is that AC wise it is ground, right? So that's the most important thing here, right? It don't have to be absolute ground. It means that it has to be AC wise ground. The reason is I don't want to use negative potential here for biasing. Okay, to make it in a forward bias region. Or other way is you can think of, I'm adding just the some positive potential, such that all the potential shifts up. Okay, so this is another way of looking into it. So what is most important is the AC wise it should be ground. It is not necessary that it has to be ground. Okay, so this is a very important fundamental understanding. Okay, so let's try to draw the common collector circuit amplifier circuit. Okay, so as I was mentioning, my collector will be connected to the VDD. Okay, so this is my collector, this is my base, and this is my emitter. Okay, okay, so now this collector will be connected to the VDD, and of course I need to do biasing, so the biasing remains the same as we have seen for the common emitter case. So I'll be biasing with two resistance, RB1 and RB2. Okay, and since I have to observe the output at the emitter, definitely I need to put a resistance here, so that I can convert the current into voltage. Okay, so otherwise if I don't use a resistance, I will not be able to see the output. Okay, so this will be my V out. Okay, and of course I need to supply my input through a capacitor, just like we did in the common emitter. Okay, this is my V in. Okay, so I'm supplying my input at the base, and of course I have my supply, which is VDD. Okay, and here we are supplying the input at the base and collecting at the emitter, and the collector is grounded, or collector is AC wise ground. Okay, the collector is AC ground, so this has to be very clear. Okay, it is AC ground, not the absolute ground. Okay, Okay, so now let's name this resistance as Re. Okay, so now let's try to see what's the gain of this amplifier. So let's try to draw the small signal circuit of this one. So first we will do the small signal circuit of the BJT. So this is my RPi, and I have my current dependent current source, which is IC equal to beta times IB, and um, this is my emitter, this is my base, and of course this is my collector. Okay, so now in this case, because this is AC wise grounded, so my collector will be grounded. Okay, and now at the emitter, I have a emitter resistance. The portion at the base remains the same like the common emitter amplifier. The two resistance RB1 and RB2 will come in parallel in the small signal analysis. And I am applying an input directly at the base through the capacitor. And of course, we are estimating the gain at the mid-bed region. That's why we are assuming this capacitor to be shorted. Okay. Okay, so now I am collecting my output at the emitter. This is my V out. So now I'm supposed to calculate what is V out my V in. Okay. Okay, to calculate the ratio of the V out by V in, let's try to level all the currents. So my IB is flowing through here, and of course my IC is flowing through this, and my IE is flowing through this. Okay, so now I'm supposed to estimate V out by V in. So let's try to write down the different equations that we have, and based on that we will be getting the ratio of V out by V in. So there are multiple ways of doing it, so you can use your own way. Okay, so what I will try to do is I will try to express V out maybe in terms of one of the current, maybe IB. Okay, so let's write it down. V out is equal to, if you see here, this is IE into RE. And what is IE? IE is basically the implies my V out is summation of IB plus IC into RE. Okay, so correct, because you know this IE is a summation of IB and IC, and we know that IC is beta times IB, implies my V out will be equal to IB into 1 plus beta into RE. Okay, so this is my equation number 1. Okay, so this is what I've got from this one. Okay, so now I can write a simple KVL in this part. So note that this V in is directly coming here, right? This is a V in voltage. So if I write a KVL on this path, what I'll get here is V in minus IB into R pi minus IE into RE is equal to 0. So this is this part. Okay, so now what I will try to do is I will try to express V in terms of IB again. Okay, the reason is so that I can divide V out by V in, and IB will get cancelled. Okay, so implies my this V in minus IB R pi, and we know that IE is just like we have expressed this one. It can be written as IB 1 plus beta into RE is equal to 0, implies my V in will be, if I take all this term this side, IB, and if I take IB common, it will be R pi plus 1 plus beta into RE Okay, so now this is my equation number 2. So if I dividing equation number 1 by 2, okay, we will get the gain, which is basically V out by V in, will be equal to, so now in this case, so the IV will get cancelled. So what I'll get here is 1 plus beta Re by R pi plus 1 plus beta into Re. Okay, so this is the expression that I will get, and this is the gain expression. Okay, so note that the expression of the gain, if you see here, I have this 2 term here and this additional term R pi. So the expression of the gain is, always lesser than 1. Okay, so it is very clear, right? So that the gain of the common collector amplifier will be always less than 1, and it cannot be greater than 1. But note that, you see, if we are coming again across this term, which is R pi plus 1 plus beta into Re, and this we have discussed in the previous lecture, that if I consider beta maybe 300 and Re maybe just 1 kilo ohms, 2 kilo ohms maybe, then this whole term is going to dominate R pi, because this R pi maybe at max it may be few tens of kilo ohms. Okay, so this is like, you can say that if Re is 1 kilo ohm and it is 300, so it is total is 300 kilo ohms, and this is just 10 kilo ohms, so it is almost more than 10 times higher, right? 10 times higher. So just like when pi is much smaller than 1 plus beta into Re, we have, okay, the gain AV is approximately equal to 1. Okay, because if it is not there, then it is 1. So, and this is the case. Okay, this is always the case. Okay, so typically this beta into Re is much larger than R pi. Okay, so this is what the condition that we will see. And if in some cases, if it doesn't satisfy, like if the beta is small, then it may not be satisfied. But typically what is observed is that the beta of the BZTs are quite large. So we will always arrive to this condition. Okay. But now their important question will come, right? So if the this amplifier, the common collector amplifier, if the gain is lesser than 1, or at max it can go to 1, so there is no point of designing this amplifier. Okay, because amplifier means it should amplify the signal. There should be an amplification, otherwise there's no use, right? If it is lesser than 1, I can just use maybe a simple resistive divider, and I can always get a gain lesser than 1. But if I need to get a gain more than 1, and then we can always use the common emitter. So common collector looks like it is not much applicable. Okay, so but however the common collector amplifier is used. Okay, so in most of the application common collector is used. Currently you may be hearing my audio, right, through the speaker or through your headphone. So there also you will see that the common collector configuration is used most of the time. Okay, so it has some other advantage, and even though the gain is lesser than 1 or almost equal to 1, but it has some other additional advantage which is not there in the previous circuit of common emitter amplifier, although it has a very high gain. Okay, so to understand the benefit of this common collector amplifier, right, that the advantages of this one, first we need to understand the input and the output resistance of this common collector amplifier. Okay, so now what we will do is we will try to approximate the, or we'll try to get the equivalent model of the common collector amplifier. Okay, CC stands for the common collector amplifier. So we have discussed about the equivalent model of the amplifier in the previous lecture. So we will try to find out this equivalent model of this common collector amplifier. And we already have found out this parameter AV. So the AV in this case is approximately equal to 1, or we can consider it to be 1. Okay. Um, and now we need to find out the R in as well as the R out. Okay, so let's try to estimate the R out first. Okay, so to estimate the R out first, what we have done is we are supposed to ground the input, right? And ground the input, right? And then we should apply a signal at the V out, then we can find out the R out. Okay, so R out calculation. Okay, so let me copy and paste the uh, circuit that we have drawn. So now as we have seen that for the calculation of the R out, as we have discussed before in the previous lecture, that we are supposed to ground it. Okay, ground the input. Okay, so my input here in this case is 0. Okay, and then I need to apply a Vx signal at the output node. So this will lead to a current Ix. Vx will lead to a current Ix. Okay, and my we know that the R out, my R out will be equal to Vx by Ix. Okay, so now let's try to estimate the let's try to estimate the Vx by Ix. Okay, so for to do that, let's try to write the KCL equation at the node E, or at the emitter node. Okay, so if you observe here, let's try to find out all the currents that is going inside the emitter. Okay, let's try to sum up all the currents. So by using KCL, right? Sum of all the currents going into a node should be 0. So this is my IB plus IC, and in this case the IE is going out, so it is minus IE. The IX is going in. Okay, plus IX is equal to 0. Okay, and we know in this case IC is beta times IB, so what I can write is IB 1 plus beta, okay, and minus IE plus IX is equal to 0. Okay, so now here basically I need to get this expression Vx by Ix. Okay, so I can write this IE. If you see here, this IE, I can write IE as Vx by Re. So implies my IB 1 plus beta minus Vx by Re plus Ix equal to 0. Since yeah, of course, since I equal to Vx by Re. Okay, so now finally what I need to eliminate this IB. Okay, so if you see here, if I want to write the IB, so this node voltage Vx is coming here. Okay, so node voltage is coming here, and IB is flowing through this. Okay, so and this is grounded. So IB is flowing towards this node Vx. So this voltage here is Vx. This voltage here is Vx. Okay, this node. So that means what I can easily write is I can easily write as IB equal to minus Vx by R pi. Okay, because the current is reversed, right? This is a Vx voltage and current is flowing this towards Vx, so the minus will come into picture. Okay, so again I can substitute IB as minus Vx by R pi 1 plus beta minus Vx by Re plus Ix equal to 0. Again, since this condition is there, IB equal to minus Vx by R pi. Okay, so now if you see this expression, I only have Vx and Ix term. So what I will do is I will take all my Vx term one side and the Ix one side. So if I do like that, then if I take all this side, my Ix will be I can take Vx common. It will be 1 plus beta R pi plus 1 by Re. Okay, so this I can write as Vx into, I can simplify this one, so it will be R pi into Re 1 plus beta into Re plus R pi. Okay, so therefore my R out, which is Vx by Ix, will be equal to R pi into Re R pi plus 1 plus beta into Re. Okay, so again we have come across this term. So as I have mentioned earlier, again that R pi plus 1 plus beta into Re, this term is going to come again and again. Okay, so therefore my R out will be approximately equal to, and if I consider beta is much larger than 1, what I can write is I can write it as R pi Re into beta into Re. Okay, since my R pi is going to become much smaller than 1 plus beta into Re, and at the same time my beta is going to become much larger than 1, so I can do this approximation. Now of course my Re gets cancelled, so implies my R out is approximately equal to R pi by beta. Okay, and of course we know that R pi is given by Vt by Ib, and beta times Ib is equal to Vt by Ic. Okay, so this is the expression of the R out. So let's try to estimate this one. Okay, so let's say IC is maybe 1 milliampere. Okay, 1 milliampere current is flowing through IC. Then R out, if we estimate this is 26 millivolt by this is 1 milliampere, which is basically equal to 26 ohms. Okay, and of course if it is higher than 1 milliampere, if it is 2 milliampere, it's going to become 13 ohms. Okay, so it's very clear that the R out is a very small value. Okay, so it is just a few tenths of ohm. So the common collector amplifier has a very small output impedance. Okay, so this is a very important conclusion regarding the common collector amplifier, that compared to the, compared to the, I should say that compared to the common emitter, it has a much smaller, output impedance. In case of the common emitter, we have seen that the output impedance is same as the RC, the resistance that we used to connect at the collector, right? To get the output, so the same, right? It will definitely be, RC has to be in kilo ohms, right? 2 kilo ohms, 3 kilo ohms, because we know that the gain of the common emitter amplifier, if we want to get a high gain, my RC has to be high, right? Because the gain is ICRC by VT, so RC has to be high to get a very high gain, so it will be in kilo ohms range. But whereas this is like, I should say that much smaller, hundreds of times smaller compared to the common emitter amplifier. Okay, so this is a very important conclusion, and this makes the common collector amplifier very important, because this we'll see in the next few discussion, we'll see that how this becomes an important factor for the common collector amplifier. Okay, so before we go ahead next and see the advantage of the common collector, we now will calculate R in. So we have calculated R out. We already know the AV. R out is very small. So let's try to estimate the R in now. Okay, and for R in, calculation is very simple. Of course, we will not collect any load here. We just need to apply a signal here and find out what is my R in. So R in calculation. Okay, so let's bring our this is the first diagram that we have used. So let's just eliminate this one, and let's try to find out, let's apply voltage Vx and find out what is the input resistance Ix, and we know that my R in will be equal to Vx by Ix. Okay. Okay, so now if you see here, the voltage Vx will definitely will come here, okay, and a current will flow through this one, okay. So and the Ix will be the summation of the current across through this resistance RB1 and RB2. So let's call it as IRB. Okay, so my Ix will be summation of IRB plus the current that is flowing through here inside, which is basically IB. Okay, the current flowing through this one is IB. Okay, so or in one sense, my Ix is going to become, this is Vx by RB1 parallel RB2. Okay, this is the current flowing through this plus IB. Okay, so this is one equation. Okay, so let's try to estimate what is IB, and we'll substitute in this equation. So to estimate this IB, I need to use the KVL here. So if I use the KVL here, then my Vx minus IB into R pi, this is the same that we did for the gain calculation, minus I into RE is equal to 0. Okay, again I'll be substituting this one as IB into 1 plus beta. So my Vx minus IBR pi minus IB into 1 plus beta into RE is equal to 0, implies I will get IB as, if I take a common of IB and take it that side and then do some simple mathematics manipulation, so I'll get 1 plus beta into RE. So let's call it as equation number 1. Okay, so then implies my Ix will be equal to Ix equal to Vx by, again, RB1 parallel RB2 plus, what is IB? IB is Vx by R pi plus 1 plus beta into Re. Okay. So now if I see here, right, therefore my Vx by Ix is going to like something like this. So y1 by 1 by RB1 parallel RB2 plus 1 by R pi plus 1 plus beta into Re. Okay. So this is nothing but you can say that this is parallel of RB1 parallel RB2 parallel of this one. So therefore my Rin, which is Vx by Ix, is going to be this whole term parallel this term. So it is basically RB1 parallel RB2 parallel, R pi plus 1 plus beta into Re. Okay. Again, here also we are encountering this term R pi plus 1 plus beta into Re. Okay. So of course now if this is like RB1 and RB2, in our discussions we have seen that this is approximately maybe in few tens of kilo ohms, and we have seen that this is hundreds of kilo ohms. So basically the whole input impedance is defined by RB1 parallel RB2. Okay, but overall it is seen, you can see here that the input impedance is relatively large. Okay, or the input impedance is in case of the common emitter, in case of the common emitter amplified was RB1 parallel RB2 R pi. The reason is because Re was 0, so that one. But now in this case the input impedance is even larger than the common emitter amplifier. Okay, so common collector CC amplifier has relatively large input impedance. Okay, now let's try to bring out the advantage of the common collector amplifier. So imagine I have some load resistance RL that I'm supposed to drive, right? And let this RL be very small. Okay, RL be very small, as low as 50 ohms, and I am supposed to drive with an amplifier, right? I'm supposed to drive with an amplifier with some amplification. Okay, this kind of scenario is very common, as I was mentioning previously, that like for example, if you are driving an audio amplifier, right? If you're driving the speaker from the audio amplifier, the speaker generally is basically it has just an inductor, okay, inductor which is wounded around a magnet, and when the signal flows, it does the vibration. Okay, so quite similar to the mechanism of the motor. Okay, so these inductors are should not have very high resistance. Okay, so and if you open a speaker, you will see that there will be an ratings like, okay, 50 ohms, 20 ohms. Okay, so this is the resistance value, and we are supposed to drive it. So imagine I have designed a common emitter amplifier. Okay, and we are trying to drive that kind of speaker. So let's consider this as a common emitter amplifier. Okay, so this is my common emitter amplifier, CE amplifier. Okay, my CE amplifier, and let's give some values. Okay, let's give some value for this R in, R out, and gain AV. So the gain, we know that it is very high, so let's consider it to be 200. Okay, we can easily get 200 gain in the CE amplifier, we have seen before. Rin, it can be as low as maybe, let's consider to be 1 kilo ohms. Okay, and the R out, we know that it is equal to RC, so let's consider it to be some value like maybe 2 kilo ohms. Okay, to get a good amount of gain of 200. Okay, now we are driving, we are having an input signal here. Okay, V in, and we are driving this output speaker. Okay, which is basically a RL. So RL, which is RL is equal to again 50 ohms. Okay, so now of course we can find out the V out here, so V in here, it will be AV times the V in is directly coming here, and we can easily find out the gain. So the new gain AV dash will be V out by V in. Okay, in this case will be a simple voltage division is going to happen here, just like we have discussed before. So it will basically be RL by R out plus RL into AV into V in, okay, or AV basically. So yeah, so we can write V out as RL R out plus RL into V in, and of course if we just divide it, then we have the V out by V in. Okay, so this is what we had seen before also. Okay, so it is very clear that because my R out is relatively larger than RL, right? So you can see the division factor, right? So because this impedance is much smaller than R out, so this term is going to become very small. Okay, so if I make it as 50 by R out, we know that it is 2 kilo ohms, 2 kilo ohms plus 50 into AV. So this one is basically, if you see here, it is 50 by 2050. So if I just estimate it, it is 1 by 41 AV. Okay, so although we have designed a very high gain amplifier AB, but there is no use because you see it is becoming 1 by 41 times then AV. Okay, so if it is 200, so approximately it is 200, then approximately it is coming out to be 5. Okay, so the gain is really small, so there is no use of amplification. The reason is because my RL is much smaller than R out. Okay, so there the advantage of the common collector amplifier comes because my R out is relatively very small. Okay, so the common collector amplifier cannot be used stand alone because the gain is very small. So what usually done is combination of the common emitter and the common collector are used together. Okay, so this is also sometimes called as cascading. Okay, CE with CC amplifier. Okay, so we will be cascading CE and CC amplifier. Okay, so again let's bring the equivalent model of the amplifiers. So this is my CE amplifier, and then I will bring one more amplifier here. So this is my CE amplifier, and this is my CC amplifier. Okay, so basically what is happening is the CE amplifier is providing a very high gain, and the CC amplifier is helping us to drive the low impedance load. Okay, Okay, so let's put this RL, and I have my V in here. Okay. Again, let's try to estimate this one considering typical values of the CE and the CC amplifier. So for the CE amplifier, we will take the same value as we have taken here. Okay. So these are the values of my CE amplifier. Let's give some, because this RIN and this RIN are different. So let's give a number one, AV1, VIN1, and of course R out 1, and this is R in 2, AV2, V in 2, R out 2. Okay, so this is my V in 2, this is V in 1, V in 1 is equal to V in. Okay, and okay, 1, 1, 1. Okay, and here let's call it as AV2. We know that it is 1, approximately 1. R out 2 is very small. Let's call it to be the previous one that we have calculated, which is 26 ohms for 1 milliampere. If we use 2 milliampere, it will be 13 ohms, even smaller. Okay, and R in 2 is, let's call it to be around 10 kilo ohms, because it is RV1 parallel RV2, or approximately RV1 parallel RV2. Okay, and we know that RL, I'm supposed to drive a 50 ohms load. Okay, so now if we just estimate this one. Okay, so let's try to go step by step. Okay, so now this V into here, what will happen to my V into? My V into will be basically a simple voltage revision, which is R into by R out 1 plus R into this point, it is AV1 into V in 1, and since V in 1 is equal to V in, I can directly write it as AV1 into V in. Okay, this is what I can directly write. Okay, and so this is V out 2 is equal to, again in this case it is RL by R out 2 plus RL into AV2 into V in 2. Okay, into V in 2, right? This node is V in 2. Okay, so if I just substitute this AV2, okay, with this one, and of course the V out 2 is same as V out, so I can just erase this one. Okay, so implies my V out, or let the V out be there. Okay, let the 2 be there. Okay, and then V out is equal to RL by R out 2 plus RL into, if I substitute this one, this whole thing here, I will get as AV2 into R into by R out 1 plus R into AV1 into V in. Okay, so therefore my final gain AV dash is equal to V out by V in is nothing but the AV1 into AV2 . So I have my R in 2, R out 1 plus R in 2 into RL by R out 2 plus RL. Okay, so by inspection also we can directly write it. Okay, but better to go step by step. So it is very clear here. So there are two voltage division happening here, but in this case RL and R out are comparable, and R in 2 and R out 1 are comparable. Okay, so although there is a this quantity is always less than 1, but it is not going to become very small as we have seen. Okay, so now just try substituting the values. So you see the AV2 is almost equal to 1, so just let's write it as AV1. Okay, so we have substituted as 1. So and this, in this case, it is R in 2 we have considered it to be 10 kilo ohms. So this is my 10k. R out 1, it is 2 kilo ohms. Okay, 2k plus 10k, and in this case it is 26. RL is 50, R out 2 is 26, plus this is again 50. Okay, let's substitute this 200 also, then we'll get the exact value. So then this is 10 by 12 into so you can see that this ratio is in the previous case we were getting 1 by 41, but this is not that much. Okay, of course there also will be a division. Now if I calculate this whole thing, we'll get approximately 109. Okay, so you can see there that the because of the division, the gain has reduced by just by half. Okay, and of course we can even reduce it by if I make it instead of 26, I can burn more current and make it 13 ohms. Okay, so then the reduction will be further very small. Okay, so yes, so and of course we can also make this one further small by increasing this 10k and 10k R in 2. Okay, we can do that. So yeah, so the point here is from 5 we have gone to 109. The reason is we have used this common collector amplifier. Okay, so the common collector amplifier, although it is doesn't have a very high gain, it's very small, but its input impedance is relatively large and the output impedance is very small, and because of which it helps us to drive a very small impedance load. So this is the main advantage of the common collector amplifier. Okay, so with this we will end our discussion on the common collector amplifier. In the next lecture we will try to understand the common base amplifier. Thank you.